Started for the next session before lunch. Before we start, I'd just say, because I don't want to forget at the end, that when we come back from lunch, just because I know there's a queue and an issue with getting back within an hour, so I think we'll start 15 minutes late, which means I'm going to eat up 15 minutes of the coffee break this afternoon. So that's an executive decision. Anyway, so yeah, sorry. But otherwise we're going to just keep going later. So that's the first thing. So we'll start back at 12 or 1:45 instead of 1:30. Okay. Anyway, so then for our last talk before lunch, it's a pleasure to have Aretha Teckentrup here. For those of you who don't know, Aretha just won the SIAM Early Career Prize in UQ, and she will give the early career talk in April at the SIAM UQ meeting. So if you didn't know it, maybe we should congratulate her. And with that being said, hope this isn't the same talk you will give in April, but so surrogate models of Bayesian inverse problem.
No, so it's going to be a different talk probably. So yeah, okay. So thanks very much, Clayton. So what I want to talk about today is using surrogate models in Bayesian inverse problems. So this is joint work with Stuart, who's now at Caltech, and Timm Sullivan and his postdoc Cheng, who are at the Free University in Berlin. So the outline of my talk is the following. So I'm going to start by introducing Bayesian inverse problems. So if you're from a statistics community, I think you know the problem as a parameter identification problem. So that's the kind of problem I'm interested in. I'm going to explain what it is and set it up. The solution to the Bayesian inverse problem is a probability distribution that's called the posterior distribution. Okay? That's usually a very complicated distribution. So if you want to use it for simulations, you can't really do that. And so you have to approximate it in some way. In particular, I'm going to approximate it using surrogate models. So then I'm going to describe how you can use surrogate models to approximate the posterior distribution. And this is very general, so this is going to be for general surrogate models. And then I'm going to discuss two examples. So one example is the Gaussian process emulators. And another example is something which is called randomised misfit models. So I hope I'll have time for the second example, but yesterday I actually put in a bit more material in the Gaussian process emulator section because I think that's something that people are very interested in here. So I might not have time for the second example, okay, but I'll try. Okay, so as I said, we're interested in inverse problems, particularly the Bayesian approach to inverse problems. So an inverse problem is just a problem where you are concerned with determining causal factors from observed results. So if you put this in mathematical terms, we want to determine model inputs based on information that we have of observable model outputs. So we have some mathematical model that models a physical or chemical or biological process of interest. You can measure the model outputs. Okay? So you can measure the model outputs. What you really want to know is something about the model inputs. However, those are usually not directly observable, so you can only observe the outputs. And so what you want to do is you want to use the information that you have on your observable model outputs to determine what the model inputs were. Okay? So these kind of examples appear in many application areas. So there's two particular examples here. So this first example is in seismology, where you want to determine the epicenter of an earthquake using observations of the seismic waves on the Earth's surface. So when an earthquake happens, it starts somewhere underground, and then the seismic waves propagate through the Earth to the Earth's surface. What you can actually measure is the seismic waves once they reach the Earth's surface. So you can't really measure what happens below the surface, but what you really want to know is where the earthquake started. And so what you're going to do is you're going to use the measurements that you have on the Earth's surface and determine where it started. Another example is in non-destructive testing. So non-destructive testing, you want to detect flaws or cracks within a concrete structure from acoustic or electromagnetic measurements at its surface. So in this application, you have some big concrete structure, and you want to know whether there's a crack inside of the structure without having to take the whole thing apart. Okay, so you don't want to really take a whole house or something apart. And so what you do is you take your structure and then you take one end and you send electromagnetic or acoustic waves through it, and then you measure what you get at the other end, and then you want to use those measurements to infer what's going on inside of that structure. Okay? So these are both examples of inverse problems where you can measure something about the outputs and you want to infer inputs. Okay, so the model that I'm talking about here is frequently in applications given by a differential equation. So here you've got the seismic wave equation, and here you've got, for example, the acoustic wave equation. So you typically have differential equations. And the things that we're going to view as inputs are something like the initial condition, the boundary condition, or the coefficients. So in this example here, the epicenter is related to the initial condition of the PDE. And in this example, the flaws and the cracks are related to the coefficient in the PDE. And so these are things that we are going to view as inputs, things that we want to learn, and things that we can observe are the outputs. So these are going to be observables of the PDE solution. So in this case of the earthquake, for example, you can measure the seismic waves once they reach the surface at a given time. So the outputs are going to be your PDE solution at given points in time and space. Okay, so if we write that down in a mathematical formulation, we get the following. So we have our mathematical model of interest. So it's a model of some process that you're interested in modeling. I'm going to denote that map by G. So this is what's sometimes known as the forward map. Okay, so this map is typically non-linear. Okay. And then the inverse problem that we're interested in, we can write it down in this form. Okay. So as I said, we have some data, some observed data, which is related to the model outputs. I'm going to denote that by Y. And we want to use that observed data Y, which I assume is finite dimensional, so it's in some Euclidean space of dimension dy. We want to use that to determine unknown model parameters. So I'm going to denote the things that we want to learn, the model parameters by U for unknown, in some space U. And so we assume that the data Y, the observed data that we have, is of this form. So as I said, the data Y is related to the model outputs, so it's related to G of U. Okay. And then we usually assume that we have some noise here. So the eta here represents observational noise, which is, for example, due to measurement error. So the instruments that you're using to take your measurements might not be calibrated accurately, or they could only give you a certain a number of significant digits, and so you have some error here. Okay. So this is the general setup. In general, this parameter space U, so the object that we're interested in identifying, the U, in general, everything works if you have a separable Banach space, so it can be finite dimensional or infinite dimensional. So you could also try to infer a function U. However, for this presentation, I'm mostly going to assume, or for this presentation, I'm going to assume that the parameters that we're trying to identify are a finite number. So they are in some Euclidean space of dimension du. I'm further going to assume that this U is compact. That is really just to simplify the notation, and pretty much everything that I say does hold for other choices of U as well. So for unbounded U or for infinite dimensional U, but just for simplicity, I'm going to assume that. So that's just a technical point. Okay. So in this equation here, we know what Y is, we know what G is, and we don't know what U is, don't know what eta is, and we want to find U. Okay. So the problem is that simply inverting the map G is often not possible. Okay. So from this equation, you can also see why it's called an inverse problem. You know Y, you want to find U, so essentially you just want to invert the map G. Okay. However, as I said, that's typically not possible. So for one thing, we don't know the value of eta, so we don't know what the value of the noise is. And furthermore, the problem is typically ill-posed, so it doesn't have a unique solution that is stable. So there could be several solutions, or there could be no solution at all. And what it means that it's not stable is the following. So if you have a small change in Y, this could lead to a very big change in your solution U. And that's something that you really don't want here, because you've got this observational noise eta. So if you just have a small perturbation eta here, you don't want that to give you the completely wrong U. Okay. So one way to get around this problem, to actually solve, to actually find a solution here, is to do a statistical approach, and particularly a Bayesian approach. And so what we're going to look for is we're going to look for a probability distribution on our unknown parameter U, given the data Y. Okay. So instead, in the Bayesian approach, you treat everything as random variables. So it's a statistical approach. So the unknown u, the data y, and the noise eta are now random variables. We then choose the prior distribution. So we choose a prior measure on our unknown parameter u, which incorporates all the information that we have. So you could incorporate something like you know that u is always positive, or you have some other geometrical constraints which you incorporate into this prior measure, which I'm going to denote by mu0, and I'm going to denote, assume that it has a density with respect to the Lebesgue measure. So this is just the PDF, which is pi 0. Okay. And once you've chosen the prior measure, you look at your data likelihood. Okay, so the likelihood of the data y is just the probability of observing the data y given a particular value of the parameter u. Okay. So that probability distribution, what form this takes, comes from our measurement model. So we again have the assumption that our data y comes from this expression here, and we now assume that our observational noise eta is a realization of a normal random variable with mean 0 and some covariance matrix gamma. Okay. If we then look at the random variable, which is y conditioned on u, if we in this expression fix u, then this is just a constant, this is a normal, and so the y is also a normal random variable, where the mean is now g of u, and the covariance structure is the same as the covariance structure of eta. And so because y given u is just this multivariate normal distribution, if we look at the density of the variable y given u, that's just the density of this multivariate normal, which is proportional to this term here. So I'm hiding the constant in front here because it's not important for our purposes, and so we just get this density here. And because I'm going to be using it a lot later, I'm going to denote this term that we have here by phi. So the phi is just the negative log likelihood of the data. Okay. Then we get our posterior measure. So we're using Bayes' theorem. So here we've got our, here we have a probability measure on u. Here we have a probability measure on y given u. And so you can just use Bayes' theorem to get a probability measure on u given y. Okay. That is what we call the posterior measure. I'm going to note that by mu superscript y. Then I'm going to assume that it has a PDF, which is given by, which I'm going to note by pi y. And by Bayes' theorem, it's just given by this. So the probability of u given y is probability of u, probability of y given u, and then normalizing constant. Okay, so we have the posterior here, the prior, and then our likelihood. And I said we have a normalizing constant here, so this constant z is just a constant which makes sure that we do have a probability measure, so we need to make sure that this density here integrates to 1, and so that's why we have the normalizing constant here, which is just the integral of this, so that the right hand side integrates to 1. Okay. You can also write it down, so this is written down in terms of densities, you can write it down directly in terms of the measures as well. Then you have the posterior measure here, the prior measure, and the Radon-Nikodym derivative in the posterior and the prior. And then you again have the same normalizing constant and the likelihood on the right-hand side. Okay, so this is just two different ways of writing the same thing. Okay. And then this posterior distribution is exactly the posterior distribution that we're interested in. So remember, in the inverse problem, we're given the data y, and we want to find u. So we now have our probability distribution on u given y, which is exactly what we were after. Okay. So this distribution is the distribution that we're interested in. And in simulations, when you use this in applications, there's typically two things you want to do. So either you want to sample from the posterior, okay, so say you want to compute some quantity of interest or something like that, so some expected values, then you typically want to sample from this posterior, and you would use, for example, Markov chain Monte Carlo methods. In other applications, you might just want to compute a point estimate of u, so you might want to compute the value of the parameter u, which is most likely under your posterior distribution, so that is known as the maximum a posteriori, or the map estimate, which is, as I said, just defined as the point which is most likely under your posterior, so it's just the point which maximizes the posterior density. Okay. Now both of those things in practice are going to be difficult because of this point here. So in our case, the computation of the likelihood phi, which is something that you have to do very many times, both in this optimization problem and when you use sampling methods, that is typically very costly. And the reason for that is if we go back to our definition of the likelihood, so the definition of the log likelihood phi, computing phi involves computing g, and remember g is our mathematical model, which is typically given by a PDE or an ODE, so evaluating g is very expensive, and so the computation of phi is typically also very expensive. Okay? So to make these kind of computations here feasible, you have to make some approximations. So in particular, what we're going to do is we're going to approximate our log likelihood phi by a surrogate model, and that is to reduce the cost of evaluating phi, and in some cases, for some surrogate models, you actually also reduce the number of times that you need to evaluate your function phi. Yeah? Okay, so that's the plan. So we now we have our true posterior, which is very expensive to deal with, and so we're going to use a surrogate model to approximate it so that we can use it in practice. Okay. So this is our true posterior. We have the posterior measure, the data likelihood, and the prior normalizing constant. What we're now going to do is we're going to approximate the log likelihood phi by some surrogate model, which I'm going to call phi n. So the n here is just an approximation parameter which governs the accuracy of your surrogate model. And we're really just instead of phi here, we're just going to plug in our approximation phi n. And then that, of course, gives us a different normalizing constant as well, because we have a different likelihood, and so that changes the normalizing constant. Okay. So at this point, the phi n here is completely arbitrary, so you can choose whatever you like, really. So I'm going to make a distinction between two types of models. Okay. So I'm going to distinguish between what I call deterministic models and what I call stochastic models. Okay. So what I mean by that is a deterministic approximation phi n. You just have, when you construct phi n, the process is completely deterministic, and you just have one function phi n that you get from your construction. By stochastic, I mean that there is some kind of randomness in the construction in phi n. Okay, so maybe these examples that I have here will make that a bit clearer. So examples of deterministic models include, for example, if you just do interpolation. So if you do something like Lagrange interpolation, radial basis function interpolation, once you've chosen your interpolation points, then that construction is completely determined, and you just have one interpolant. You can also do something like regression, and then there's these methods which come more from the reduced order modeling community, like things like proper orthogonal decomposition and things like that. So those are deterministic models. And stochastic models, I guess one of the simplest examples you can think of maybe is the example that I've given here. So even if you do Lagrange interpolation, once you choose, for example, random points, which is not a good idea, but you could do that. Once you choose random points as your interpolation points, the process that you're constructing is no longer completely deterministic. Yeah, so the interpolant that you end up with, a surrogate model, will depend on the randomness in these points here, and so you have some randomness or some stochasticity in your approximation. The same is also Gaussian process emulators. So we've heard a lot about Gaussian process emulators. The Gaussian process emulator is a Gaussian process, so it's a stochastic object, a random object, so you again have a random surrogate model. So these are kind of statistical ways of doing interpolation and regression. Another type of method where some stochasticity is usually involved is in projection methods, in particular randomized projection methods. So if your input space or your output space is very high dimensional, you might want to project it onto a lower dimensional space, and in that case people very frequently use random projections because there's better algorithms and they usually have better properties. So you end up projecting onto random subspaces, and so again you have some randomness in your construction. And the example that I might talk about later, these randomized misfit models, you actually project the observation space onto a random low-dimensional subspace. So I hope that distinction is clear. Okay. So as I said, at the moment the surrogate model is still completely arbitrary, so you could use either of those. And what we're now interested in is a general convergence theory. Okay, so we're using this approximate posterior here to approximate our true posterior, and so we want to know how well we're doing, what is the error in this approximation. Okay, so we have to choose how we're going to measure the error, and for that we have chosen to use the Hellinger distance. If you're not familiar with the Hellinger distance, it's just a way of measuring the distance between two probability distributions. Okay, so here we have the true posterior, the approximate posterior, and it's defined in this way. So here you see you've got the ratio of the posterior to the prior density. So here you've essentially got the likelihood of the data under the true posterior. Here you've got the likelihood of the data for the approximate posterior. And so you're comparing the two likelihoods, and then you're kind of integrating over the parameter space. So it's kind of an averaged difference between the likelihoods in the two distributions. So the reason that we like the Hellinger distance is that it automatically gives us a bound on the total variation distance, and it also gives us a bound on the error in expected values. So if you have the function f that's square integrable, both with respect to the true and the approximate posterior distribution, then you can bound this error in the expected values directly in terms of the Hellinger distance, which is also nice. So now, first result that I have here is for these deterministic surrogate models. So where the surrogate model is really just a deterministic function that you're constructing. And then we have the following result. So we can show that you can bound the error in your posterior distribution. So this is just the distance and the particular Hellinger distance between the true posterior and the approximate posterior. You can show that you can bound that directly in terms of the error in phi. So you're approximating phi by phi n, so you've got this error here. Particularly it's measured in the L2 norm over the parameter space and then weighted by the prior. So it's weighted by the prior in your Bayesian inverse problem. All you need for this result to hold is the following. So you need to assume that pointwise in your parameter space the approximation doesn't blow up. Okay, so you just need this quantity here to be bounded uniformly in n. It doesn't need to converge as n tends to infinity. All you need to make sure is that it doesn't blow up to infinity as n tends to infinity. So this just needs to be bounded. And so that applies to very general surrogate models. The reason that you need this assumption here is that you can use it to prove this. So then you can prove that the normalizing constant of the approximate posterior can be bounded independently of your parameter n, both from above and below. And this then tells you that this constant c here, so this constant c heavily depends on this normalizing constant. And so then this c here can be chosen independently of n. Okay? So that's what you need this assumption for, and then the rest really just follows from the local Lipschitz continuity of the exponential function. Okay. So that was the result for deterministic surrogate models phi n. Okay. So when you have a surrogate model that is in some way stochastic or contains some randomness, then you actually have to think a bit about how you want to define your approximation to the posterior. Okay, so if you do the same as we did before, you just plug in your approximation phi n here, then we've got this random parameter, so I'm using the omega here to indicate the randomness, so it's the random parameter in the construction of your phi n. If you do that, because the phi n is random, you will get a random approximation to the posterior. Okay. So if you don't want that, then you can get a deterministic approximation of your posterior either by fixing omega. So if you fix omega here, you just take one realization of your random surrogate model phi n. So that would give you a valid approximation. Or you can also take what we call the marginal approximation. So the marginal approximation we're integrating out over omega. So here we're taking the expected value with respect to omega of the likelihood here. And then the correct normalizing constant is in fact just the expected value of the normalizing constant that we had here. Okay. So those are two different approximations that you can then use which one you want to use very much depends on the type of approximation that you're using. So in some cases, this one where you just fix omega, so you just use one realization, is appropriate. So for example, if you're doing these random projection methods, then you typically just project down onto one low-dimensional subspace, and then you use that as your surrogate. You typically wouldn't want to average over different ones. I mean, you could if you wanted to, but so that's typically used there. And this one, yeah, you can also use that. Okay.
Can I ask a quick question? The randomization distribution is independent of anything else on the blackboard, so shouldn't you be taking the expectation of 1 over z rather than 1 on the expectation of z when you're normalizing?
Sorry? So you want here, you want the expectation
Shouldn't it be expectation of 1 over z rather than 1 over the expectation?
No, so you want to still make sure that this is a posterior, as this is a probability distribution. So if you look at this right-hand side, so this one, so you need to make sure that this still integrates to 1, and if you want it to integrate to 1, then this is the correct normalizing constant, and not the expected value of 1 over z. So for these two approximations, we now have a very similar result. Okay, so if we look at the final results first, we again can prove bounds on the error that you're committing by approximating the posterior. We have the true posterior, and then this marginal approximation where we're integrating out the randomness in phi. The error bound that you get is this one. So again, we have the L2 norm over the parameter space weighted by the prior, and then we have the error between phi and phi n here, and in particular we need this moment of the error here. The r that you can choose depends on the regularity of your phi n. So the distribution that you have for phi n is going to give you the value for r. For the random approximations, we have the following result. So because this random approximation still depends on the randomness in phi n, this is still random, and so here we're taking the expected value, or the second moment of the Hellinger distance, and then you get this term here. So it's essentially the same that you have here, just that you need a higher moment for the error. So here you need the 2r, where the r is the same as here. Okay. So those are the final results. The assumptions that you need are firstly this one. So this is very similar to the result that we had previously, that uniformly in the parameter space you need to be able to bound this term. So you need to make sure that this term doesn't doesn't blow up as n tends to infinity. And then you need some regularity assumptions on the distribution of phi n. Okay. So this is a bit vague. So if you write down the assumptions, it's a bit technical. But so the regularity assumptions that you need are essentially this. So you need to have some regularity on the distribution of phi n, which are sufficient to prove moment bounds on the normalizing constant. Okay, so what you really need is you need to be able to show that the expected value of the normalizing constant raised to both positive and negative powers is bounded, so it has to be finite, and moreover it has to be bounded independently of n, and you need to be able to do that for some p greater than 2. Okay, so that is really the crucial thing, and that is what I mean by these regularity assumptions here. You need to have some control on the distribution, and in particular on the tails of your distribution of phi n, so that you have this result, so that you can bound these constants c1 and c2 here also independently of n. Okay. So once you have that, then the rest of the proof is again just the local Lipschitz continuity of the exponential function. Okay. So I'm now going to go on to examples. Does anybody want to ask any questions?
Just with the way you expertly introduce the problem setting, right? You had this assumption that the observational error was Gaussian, and you put this gamma, and then this gamma will induce the metric on your norm, right? Mm-hmm. It will induce your norm. So if you put it like this, I then think, okay, phi is some kind of Gaussian process, right? Are you relaxing somehow the fact that you said eta were Gaussian in these things, or you are actually exploiting the fact that eta is Gaussian?
No, so we're not exploiting this fact at all. So we're really just using that our likelihood has this form. So all we're assuming, so we don't even need that this is Gaussian. We're really just assuming that our likelihood is the exponential of phi for some phi. Whether this phi is this quadratic here, like for the Gaussian, or whether it is something else, it really doesn't matter. So we're not using that explicitly anyway.
Thank you. Why are you emulating phi and not g?
So we have done both. So we have theory for both. It's easier to emulate phi because it's a scalar quantity. So the g is typically a vector quantity, so then you have to choose how you choose the emulator, in particular if you choose just a diagonal covariance structure, so whether you emulate just all the entries in g independently or whether you introduce some correlation between the different entries, so it's just a bit more complicated, but we have theory for that as well. And the results look exactly the same.
Can I ask a follow-on question? Phi has a square in it.
Mm-hmm.
So it has an inherent non-stationarity. As your u gets farther from the best u, the errors amplify. Doesn't that make surrogate modeling, say by Gaussian processes, much more challenging?
I haven't thought about that. I don't know. I have to think about that.
But again, this is a prior on eta. It's exactly what I'm asking. So if you believe eta is not Gaussian, you shouldn't use a model that models P as a Gaussian process. So yeah, if you know eta is not Gaussian, then it doesn't make sense to have a Gaussian process there. It's a prior mismatch, what you will introducing by using a Gaussian process.
I think it is non-Gaussian because of the square.
Well, it depends on your setup. Yeah?
But just a question, just to clarify for me. So, when you take the random version of your emulator for the quantity, and then you create the marginal version. Okay. So in the margin, you write down the show me. Okay. So when you take that expectation, okay, that is expectation over the distribution of omega. Yeah.
Yeah. So over the distribution of phi n.
Distribution of omega conditioned on y.
We're assuming that the randomness here is independent of.
When you see y, that might give you information about omega. I've worried about this quite a lot, which is why I'm asking you.
I think it does.
Yeah. I tend to not do it conditional on y, but I tend to feel that I'm making a mistake here. We should maybe talk about that after.
Yeah. Again, that's something I've never really thought about. So, yeah. Okay. Good. Okay. So we now have these general results, and if you have a particular surrogate model, then you need to check that you have these regularity assumptions that I have here, so that you can apply these results here. So one particular model which where we applied this was in Gaussian process emulators. So the phi n is the Gaussian process emulator. We've already heard a lot about Gaussian process emulators in this workshop here. So I think most people know what they are. So it's also known as Kriging in the geostatistical literature. And the way I see it, it's kind of a statistical version of doing interpolation or regression. In the particular setup that I'm going to show, it's interpolation. I should say it's also quite a simple setup for Gaussian process emulation, where you can do more general things as well. So just to recap very briefly how it works, you have your function phi that you want to approximate. You view it as a sample of some Gaussian process with some mean and some covariance structure. The mean and the covariance structure that you have here will depend on what your phi is. So it's typically chosen to reflect, say, the smoothness and the typical length scales that you know that phi has. So you might know that phi has a certain number of derivatives, which you would then incorporate into this kernel. You might also know something like the typical correlation length, or on which kind of length scales it varies, whether it's like really smooth or whether it varies on a very short length scale. So you can incorporate all of that into the kernel and the mean. What you then do is you evaluate your function phi at a set of points, which are called the design points. So these are capital N points. So n here is the number of design points. And then you evaluate your function at those points, which gives you these function values. And then you take your original model phi 0 that you have here, and you condition it on these values here. by the property of Gaussian processes, that gives you another Gaussian process. So this phi n is again going to be a Gaussian process. It has a different mean and a different covariance structure to your original one, but you can write down the equations explicitly, so you know what the mean and the covariance of this Gaussian process is. Okay, so this is then the Gaussian process emulator phi n. And this is just a brief recap. Okay, so the result is then the following. Okay, so this is then the application of the general theory that I showed before to particularly Gaussian process emulators. So if you consider just using the mean of the Gaussian process emulator as your surrogate model, that's a deterministic surrogate model, you can then show that the error between the true posterior and your approximate posterior can be bounded by this norm. So then you have the difference between your true function phi and the mean of the Gaussian process emulator in the L2 norm. For the other approximations, so for the marginal approximation and this random approximation, you then have these bounds, and so this parameter r that we had here earlier, in this case you can choose anything larger than 1. Okay?
Can I ask a question?
Yeah.
It's probably a follow-up to the couple that went on before, but because your Gaussian process isn't, you can't make it strictly positive. Does that result sort of assume that it is?
No. So you can deal with that as well. It's not a problem.
So the GP could give you negative estimates.
Mm-hmm. Yeah.
But that one still holds.
Yeah. So that is one. That's the reason why we're emulating the log likelihood rather than the likelihood directly. So if you would try and emulate the likelihood directly, which other people have done as well, then you get problems with being positive and negative, and then they have to constrict it to being positive. But here, because we're emulating the log likelihood, it's not a problem that the emulator takes negative values.
Sorry, I just get a bit confused. So the first expectation there is the conditional expectation, which gives you the surrogate fit, and the second expectation is respect to the randomization distribution.
So these are both expectations with respect to the distribution of phi n. Of the distribution of phi n.
Okay, so with the random surrogate, yeah, I'm still there's no randomization. When you do random sampling, is that, where's the randomness? I would better talk later to some. Those are the same expectations.
Yeah, so the randomness comes from phi n. So here, this quantity here is random because phi n is random. So this here is random, and it's random because it depends on phi n. And here you're still taking the expected value with respect to the randomness in phi n, which is the same that you're doing here. Okay. So these are the general results that we have. As I said, we have these regularity assumptions that we need, and essentially what we needed for the regularity assumptions was to prove bounds on the normalizing constant. So maybe if I just go back. So here we have these regularity assumptions where we needed to be able to show this. Okay. So something I didn't say before was that this r that you get here and the p here are closely related. So roughly speaking, the r and the p here are conjugate exponents. So the larger you can choose the p, the smaller you can choose r here. Okay. So for the Gaussian process emulators, what we could show is that we have this result for any p less than infinity, which is where we get any r greater than 1 in the previous result. So we can show this, that the both positive and negative moments of the normalizing constant for any p less than infinity can be bounded independently of n. Okay. So for that you use the fact that you know that these things converge. I'm going to comment on in a minute. The really crucial part is using tools from stochastic analysis. So in particular you use Fenech's theorem. So if you think about it, the normalizing constant involves the likelihood. The likelihood is the exponential of minus phi. And so if you want the normalizing constant to have moments, you actually need exponential moments on the distribution of phi. Okay. So in the case of Gaussian processes, Fenech's theorem tells you that you do have exponential moments for Gaussian random fields. So you use this Finik's theorem, but then you need to make sure that all the constants that appear in Finik's theorem can be bounded independently of n, and so you need a bit more tools. So you have the Sudakov-Finik inequality, which is a comparison inequality between Gaussian processes, and then you have a Borel-Tiss inequality, which is a kind of large deviations result. Okay. So that's what you need to prove the bounds that we have here. Okay. So now what you have to be able to do is you have to be able to bound these here. So what you would be interested in is bounding the quantities that we have here, so this error, and this error, in terms of n. So proving some rates in n for these terms here. Okay. So that's what we're going to do now. The way that we do it is that we use a lot of results from scattered data approximation or radial basis function interpolation. Okay. So you can show that these Gaussian process emulators are very closely related to scattered data approximation. In particular, if the covariance kernel k that you use to construct the Gaussian process emulator is stationary, then it's very closely related to radial basis function interpolation. So in particular, if the original Gaussian process phi 0, which you assume that your true function phi is a sample from, if that has mean 0 and then this stationary covariance kernel, so the covariance kernel k depends only on the distance between 2 points, then you can show that the mean of the Gaussian process, so the mean of the Gaussian process emulator phi n, is just a radial basis function interpolant of phi. Okay. So that means it has this form here. So it's a linear combination of these kernel functions, which in this case are radial basis functions, where the coefficients are explicitly known. You can write them down. And furthermore, if you look at the expected value of the Gaussian process emulator at the points un, so the points un were the design points, so at the points where you did evaluate your function phi to construct the Gaussian process emulator, you just get your function phi of un back. Okay? So un are the interpolation points, and so you really just have a radial basis function interpolant. Okay? So if you here don't use a zero mean, then you still have an interpolant. So this condition is still true. Here you get something which has this term plus something which is related to the mean. Okay? So it's a very similar expression, just that you here have some additional terms which are related to the mean. If your covariance kernel is not stationary, then again you still have an interpolant which is exactly of this form, just that this here is not a radial function, so it's not a radial basis function interpolant, but it is still a kernel interpolant. Okay. So then under certain regularity assumptions, both on the way that you choose the design points d and the regularity of your true function phi and the regularity of the Gaussian process emulator phi n, what you can show is the following. So you can show that the error between the function phi that you're approximating and the expected value of the Gaussian process emulator goes to 0. Okay. And the variance of the Gaussian process emulator, or the standard deviation of the Gaussian process emulator, goes to 0. Okay. So you can say that the Gaussian process emulator phi n tends to the true function phi as n tends to infinity, exactly in this form, in that the mean of the emulator tends to the true function and the variance in the emulator goes to 0. Okay. So in particular, I'm measuring everything in the L2 norm, because we saw previously that the L2 norm is the norm that we're interested in for our error estimates. Okay. So the rate of you can prove rates of convergence here as well. The rates that you get depend very much on the regularity assumptions, so how you choose d and what regularity you have here. I'm going to show two particular examples, which I think are frequently used, but I do want to emphasize that there are error estimates for a very wide range of scenarios. Okay, so in this book here, by Holger Wendland, which is called Scattered Data Approximation, there's a very general theory for interpolants of this form here. So in particular, also for non-stationary covariance kernels, so you don't need stationary covariance kernels for this theory to hold. Okay. So as I said, I now want to discuss two particular examples of choosing the design points d and the regularity that we need to assume on the function phi. Okay. So the first one is using Matern covariance functions. Yeah, so we've seen these, or these have been mentioned a couple of times before as well in the workshop. So the Matern covariance looks something like this. So it looks a bit complicated, but it essentially has three parameters. So there's this sigma squared, which governs the marginal variance. Then you have this lambda, which is kind of a correlation length parameter. And then you have the nu, which is a smoothness parameter. So the higher you choose nu, the more smoothness you impose on your Gaussian process. Then for the design points, you can choose anything that you like. Okay, so for a general set of design points, we're going to define what's known as the fill distance. The fill distance is defined in this way. It's the supremum over all points u in your parameter space u, the infimum over the design points un of the distance between u and un. Okay, so the fill distance is really just the radius of the largest ball that you can fit in your parameter space u, which doesn't contain any of the design points. So it's a measure of how uniformly your design points are spread. And in particular, if you want this fill distance to go to 0 as n tends to infinity, then you need a space filling design. Okay. So to give you some idea for how this fill distance depends on n, then if you have a quasi-uniform point set, the fill distance will typically go like n to the minus 1 over du, where du was the dimension of u. So there's quite a bad dimension dependence here. So if you have that, you can show the following. Okay, so you have some technical assumptions on u, but then you can show that this error between the function phi and the mean of the Gaussian process emulator goes at this rate here. So you get a rate in terms of the fill distance. You can also get a rate for the standard deviation or the variance of the Gaussian process emulator, again in terms of the fill distance. So this result here is for functions phi, which have this smoothness here. So this space here is the Sobolev space of smoothness nu plus du over 2. Okay? So the reason that this particular space pops up here is that that is the reproducing kernel Hilbert space of the Matern kernel. So this is quite a strong smoothness assumption. However, you can prove results as well for functions which are not in the reproducing kernel Hilbert space of the kernel. So as long as you are in some Sobolev space h tau, where tau is greater than du over 2. So this essentially means that you have to have continuous functions. So you have to be in a reproducing kernel Hilbert space. So you have to have continuous functions. But as long as you have this regularity, you can also prove rates, although they are lower than the one here. So you get a lower rate which corresponds to the smoothness here. Okay. So that was one particular example. As I said, because you have this here for quasi-uniform point sets, you get quite a bad dimension dependence in the results here. Okay? So you've got the 1 over du here, so you get quite a bad dependence on the dimension. There are some very new results which alleviate this in some way. Okay? So what we're going to do is, instead of using this traditional Matern kernel, we're going to use what sometimes called the separable Matern kernels or tensor product Matern kernels. Okay, so the way that you construct these is you just take a tensor product or a product of one-dimensional Matern kernels. Okay. The ui here is just the ith element of u. So you have du of these, and then you just take a product of du Matern kernels. Okay. Because this Matern kernel has this tensor product structure, you also need to assume a tensor product structure on your domain. So for simplicity, just going to assume that your domain is this hypercube from -1 to 1. Okay. Then this time we're going to choose a very particular set of design points. So we're going to choose our design points D as a Smolyak sparse grid based on Clenshaw-Curtis points. Okay. If you do that, then you can show the following. Okay. So again, you have an error bound on the error between phi and your mean of the Gaussian process emulator phi n. And then you get this complicated expression here. The norm that you have here is again the native space or the reproducing kernel Hilbert space that corresponds to this kernel here. Okay. And you can see, so you do have some dimension dependence in the log term here, but the leading term here, the rate that you get in n here, is completely independent of the dimension. Okay. So it doesn't completely get rid of the dependence on the dimension, but it does have a much better dependence on dimension than the one that you had previously. And for the variance, you can show something very similar. Okay. So I think I probably won't have time for the second example. So just very quickly, in the second example, these randomized misfit models work where you have a very high dimensional data vector, so your observed data y is very high dimensional, and you project it onto a random low dimensional subspace. So that's how the randomness enters there. I don't think I want to go through the details, but essentially we then also again can show convergence in this case. So we again have the application of the general theory here, that you can bound it in terms of this, and then essentially it involves a Monte Carlo approximation, so this is where the square root of n comes from here. But if you're interested in that, then you can come in and talk to me later. So just to conclude very briefly, so what I showed or what I discussed was how to use surrogate models to obtain computationally cheaper approximations to Bayesian posterior distributions. Then I showed that the error that you're committing in the posterior distribution, in particular measured in the Hellinger distance, so the Hellinger distance between the true and the approximate posterior can be bounded directly in terms of the error of the surrogate model, measured in a suitable norm. And the theory is really very general, so both in terms of the mathematical model G involved, so we didn't make any assumptions on whether it's a PDE or ODE or what type of PDE or ODE, and also very general in terms of the choice of surrogate model. And then I wanted to point you a bit to the literature. So this is the paper where they discuss these randomized misfit approaches, which I didn't really have time to talk about. This is the paper with Cheng and Timm Sullivan, where we give a very general framework for using random approximations to the log likelihood in Bayesian inverse problems. If you're interested in learning more about these Gaussian process emulators, there's this book here by Chris Williams that's freely available on the web. This is where I got the results for sparse grids from. This is the paper with Andrew, where we considered the use of Gaussian process emulators in Bayesian inverse problems. And this book here by Wendland, if you are interested in any kind of theory for kernel approximations, or you want to know anything about positive definite kernels, then this book is really, really good. So I really can't recommend this book enough. So it's called Scatter Data Approximation. Okay, thank you.
I have two questions actually. The first one is, do you have bounds for emulating subsampled likelihoods? And that's my first question. And my second question is there any theoretical guarantee or like incentive for using the MCMC samples to do the adaptive design of the emulators?
So the first question, I'm not really sure what subsample likelihoods
I mean, like
are.
let's say you have your data is a tall data, and you take a sample of that data, not the entire data, and build your emulator on that, and then you.
Okay,
Yeah.
so that would be a particular example of.
Yeah, so I'm saying like.
Yeah, so I haven't looked at that, but I would guess so. It would probably, if you can satisfy the regularity assumptions, then you would be able to apply the general theory. So then you would have to be able to bound wherever is on the right hand side here.
Yeah,
But I
for
think in
like
general.
big data problems that would be quite useful actually.
Yeah. And sorry, the second question.
The second question is like, what sort of incentive is there to use the MCMC samples to do adaptive design of the Gaussian like emulator?
Yeah, so I think
Because like for like let's consider an unidentifiable model on a huge big like lots of dimension, and we want to sample that sort of posterior distribution. So is it useful to follow the chain and do sort of optimal design following those sort of patterns?
Yeah, so I think in general that is a very good idea, because if you're looking here at the Hellinger distance, you've got the these two terms here. So the in areas where your posterior density is very low, then this integral here is going to be very small, and so you don't really need to put a lot of points there.
Exactly.
So I think in general, yes, but there's not a lot of theory for that at the moment.
Thank you.
That was very nice, but you've assumed that there's no discrepancy in the model, that the model's perfect. Can you extend it to include the model discrepancy test?
So do you mean in the construction of the Gaussian emulator or in
No,
the
in the
framework?
original theory, you have that the expected value of y is 0 and that the model gives the same thing that the expected value of y gives. If the model's wrong, if there's an error in the model, so the model doesn't reproduce reality 100%, then this doesn't hold.
Yeah, that's true. So all the analysis is based on this equation, but we assume that the data really comes from the model, and if that model is wrong, then yeah, there's a problem. So I think that's something which people don't really fully understand yet. So in that case, you end up with problems with identifiability. So I think there is work going on at the moment in the last couple of years where people try and address that, but I'm not that familiar.
In principle, you could incorporate it in the distribution of eta.
Yeah.
It was general fine, but it's not straightforward.
I have a really follow-up question. So it's exactly this point. So you play the game of, let's assume, properties of the induced distribution, right? The gamma minus 1 thing. This when you choose your kernel. What about if you have actual information or beliefs on eta, on the distribution of eta? How these results relate to that? Because here you're fixing, in a way, your kernel for your Gaussian process, in a way, inducing an assumption on eta, right? By the covariance precision relation method, right? So I wonder if you have actual information on the eta or beliefs on eta.
Well, what we're looking at the moment is when you, in this step here, so for the initial Gaussian process that you use, we're looking at using, if you use the Matern kernel, you have these hyperparameters, and we're inferring the hyperparameters from the function evaluations as well. So we're using this function evaluations to then infer what the mean and the variance is, and in that case, all the theory goes through.
So
Are
you're
the same.
inducing like that a distribution eta. By doing that, you're inducing a distribution. And what happens if you actually know something about the distribution of eta? Can you bring it back to this side of this thing?
I would guess. So I mean, there's nothing stopping you from doing that. So the way that you specify the kernel here,
I'm more interested in the sampling results you have. So because your sampling results depend a lot on what kernel I put there. But if now I'm not free to choose this kernel, I'm forced, or let's say somehow loosely forced, because the expert or my simulation show me there is this discrepancy or this particular distribution on the error, how can I use your sampling results to somehow at least hope that there will be convergence in that case?
I have to think about that.
Two last ones quickly.
Just a very quick one. Again, I'm struggling with expectations. So, the fit for psi is a conditional expectation. So, it's a conditional. The fit, the emulator, is a conditional expectation, conditional on the observations that were designed. So, so the asymptotics has to be interpreted as conditional on observations. Not a kind of unconditional expectation. So it might be good for idiots like me to put conditional expectation in, then we know that it is that and is that. I mean, you keep saying expectation, but it's always the conditional expectation given the observational data. Just to
Yeah, so I haven't really been very precise about that here.
and then you have other
I
expectations.
mean, really here, this is also a distribution on u given y. So I'm kind of hiding that in the y here, but it's really also conditional.
It's a minor point, but it does that does help, I think.
Okay.
Ask a question.
Yeah, just wondering, so there was a convergence result of Marzouk, thanks to you, on the convergence of the posterior different convergence of the surrogate for the same likelihoods as you are doing. But they measured in the Kullback-Leibler divergence.
Yeah, so they measured the Kullback-Leibler, and they only.
Major difference, or is it because you also look at the stochastic processes? Or?
So they didn't look at stochastic approximations. They only looked at deterministic approximations. And yeah, they did the Kullback-Leibler. So the reason why we're doing Hellinger is this reason here. The Kullback-Leibler does not give you a bound on the error in expected values. But I mean, there's some people prefer Hellinger, some people prefer Kullback-Leibler. But I mean, all the results that we did, and in particular these results for the random ones, you can also extend them to the Kullback-Leibler divergence.
Okay, but the main novelty is in the stochastic part of
Yeah, the main novelty is in the stochastic part, yeah.
Okay, so Nicola, thank you, Aretha.